that's not trying to think about everything else with respect to the class at once. So a couple of housekeeping, class-keeping notes. So if we do a quick screen share on our beloved website, Technology Rediscovery, just want to point you to how I've organized my office hours. So officially, here at our site, the very top is my life schedule. Monday, Tuesday, and Wednesdays are pretty busy. So in the middle, I've got my office hours posted. So the office hours that pertains to us most is 5 to 6 right before class. And so if you were on a little bit earlier, you will have seen this on my screen, which hopefully will become a regular. So it says, if you have an office hour question, just chirp in. So what I'll do is I'll keep my speakers on and try to log into Zoom as close to 5 o'clock, 1700 as I can. And if you've got a question, you can pop on early and we can work through it. As usual with me and the way my life tends to work is I'm reevaluating and planning and prepping. So if you don't have a specific office hours like question and you just want to chit chat, I love chit chat, but let's do that after, because I'll usually be in a state of frenzy. And that's just a product of the way running 6 classes and designing data analytics works for me. So I apologize in advance. I will be as present as I can, and just note that office hours is there. And then as you see on the schedule, as they say across the Atlantic, you can pop into any office hours you want. And so I've got 6 hours worth during the week. Any questions on that? Great. Take a moment and submit your attendance if you haven't. So private chat me your public name and the number of minutes that you spent on data analytics this week. 0 is fine. If things got busy, I don't want that to feel like, I want it to be an encouragement of accountability, but not a source of anxiety. Remember, my use of that information for this term is entirely internal. It will not be associated with your grades. I will not publish a spreadsheet. By the end of the term, I think I'll ask if we want to, if you'd like me to run some summary analytics, I'd be happy to do that, but I'll only do that with class permission. Okay. So encodings. So let's reframe to that. I encourage you to get paper and pen. Your brain loves to write. Like I say, in-person classes, even if you ball it up and throw it in the trash, it's certainly, taking notes is certainly not for naught. It's certainly beneficial to your brain because it helps tactilely insert data into memory. So let's back up and reframe a little bit. Let's review where we came from last week and see where we are. This is Data 102. We are, my goal is to create a, hang on, I'm adjusting my views. So one of the downsides is I can't record me as full on the screen and see all of you at the same time yet. So I'm kind of juggling that. So my goal over this term is to give you a high-level exposure to the kinds of concepts that you might run into being a data analyst in any capacity. And what we started last week was, well, how would we classify the kind of data we're interested in? And so we made a quick little tree that divided data in the world into some secondary and subcategories related to that. And let's just quickly review what those were. So the 2 major divisions that we see in data are what? We'll go fast on this. It's good to get our brain back.
Qualitative and quantitative?
Yep, so we have qualitative data, which is, we'll say, this is relatively computer computer unfriendly, and we'll discuss why that is tonight. And computers are much better at which type?
Quantitative data?
Yeah, the quantitative. So we would think of this as numeric, and at its basic form, numeric data in computer is stored how?
As ones and zeros?
Yeah, well, we would symbolically represent as
Integer?
ones and zeros. Who said integer?
Monica?
Monica. Hi, Monica. Yeah, so an integer would be a very basic derivation, or a basic unit of numeric data. A computer doesn't even know about an integer. What computers only know about are strings of voltages, either voltage present or voltage not present. And so when we think of binary, we could symbolically represent no voltage as a 0. So we could say no voltage, and a 1 as voltage. And how many volts are we talking about down in a processor? Any guesses? Any electronics folks out there? I know you're out there.
I'm going to take a wild guess and say it's either 5, 3.3, or 9.
Here's someone that's using Arduino, haven't you?
Yes.
Yes. So the magic number in modern electronics is 3.3 volts. So something you can't even, you couldn't feel 3.3 volts. Generally, we think of if your fingers are conducting well, you can sometimes feel 9 volts. If you put some salt water on your fingers, you can almost always feel 50 volts. So what we're really saying is a computer is capable of understanding only a series of voltage and non-voltage pulses. And so you've heard of a computer processor as labeled in gigahertz or megahertz when they were earlier processors. A hertz is 1 cycle, if we had to draw a sine wave. So if we said this is a 300 megahertz processor, what we're saying is every second we have a clock chip in the computer that ticks at 300 beats per second, and your computer's processor is capable of completing, we would say, 1 processor cycle, or we might say eating one word, as the language is, every tick of the processor. And so as computer processors have become more complex, they are capable of churning longer and longer sets of 1s and 0s every clock cycle. And so all of our quantitative data, all the quantitative types, can be encoded in sequences of 1s and 0s. And so what the earliest processor, how many, each one of these 1 or 0 is called a what? Computer folks. Ryan, you can't answer. Sorry, you got to buy.
Was that a bit?
Yeah, 1 bit. So each 1 or 0 compartment we would say is a bit, and 8 of those together gives us a
Byte.
Byte. And so that's our, we'd say the basic word size, 8 bits equals 1 byte. That would be our fundamental unit. And so processors now are designed to eat, if you will, multiples of bytes. And so now what's a common processor? How many bytes can it process each cycle? Who's installed something recently? You'll often see this number in installation files. They'll say Windows
64?
Yeah, 64. So we now can, a modern processor's word size is 64 bits per word. And it's a little bit crude, but this isn't a computer science class, but you are data analytics folks, and so computers are your tools. So I will never shy away from tool specifics, because you'd be surprised at how quickly you can get down to the bit level. One example of this was when I was processing data with CreateLab, and we were sorting through raster satellite image tiles of the Earth, trying to detect solar panels. We were asking, can we detect a country's solar usage with satellite imagery? So what we were dealing with is individual pixels of a satellite image, each of which was encoded with, we would get 2 bytes per layer of color, and we had red, blue, green, and infrared per pixel. And so it wasn't uncommon to actually look at screens of raw pixel data to make sure that our tools were doing it right. So lest you think this is unnecessary, I believe it's critical. So we're dealing with 64-bit words, and so any quantitative data types, we had, someone said integer. What were the other ones we talked about?
Floating point. Floating
Yeah,
point.
floating point. And so binary would be, what else?
True and false.
Boolean.
Boolean, yeah.
Yeah, Boolean, yep, true and false.
And US, is that floating point?
Yes, floating point. Sorry, it's a little bit crude because we're trying to go fast. So all of these numbers are eventually reduced to ones and zeros. And so our activity to start tonight is an encoding scheme is a way of connecting or coordinating. If we want to represent anything but a 1 or a 0, we have to have a way of translating the raw binary data that a computer copes with into something more useful, any other data type. And so let's just start with some fundamentals. If you'll join me on the site, remember F5 is your friend. So I was updating this moments before. So if you had this loaded earlier, you'll want to do a refresh. Let's do a share screen and we'll jump down. So remember, all of our links for a session are going to be inside the schedule or schedule. So I posted the videos from last week. So I apologize for the quality. I realized this mistake that I made with, if I don't say pin video, then my recording gets all of your little videos in a tile. So I blew up my little tile as big as I could and then tried to purple all of you out. I may have missed a moment or two, and I apologize if it's concerning for any. No one was picking their nose or anything embarrassing like that I saw, but I blinked them out anyways. You can pick your nose if you want. You can do whatever you want with your finger. Anyway, so let's do an F5. Oh, look, they appeared. So join me here. Binary hex decimal converter. This is from a site called Math is Fun, which is a great little site. It looks kind of silly, but it's actually fantastic. And it's the lowest add converter that I can find. And I think this is run by one human, and they deserve the work. So they have lots of cool math problems up here. So in a computer, let's say I teach 6 classes at CCAC. A computer doesn't know what a 6 is. It only knows 1s and 0s. And so at the crudest representation, a base 2 encoding and binary of the decimal encoding of 6 is 110, or on, off, or we could think about it as voltage, voltage, no voltage, and we'll get to hexadecimal in a second. So we could try typing in other numbers like the current year, 2020. A computer doesn't know what a 2 is. What it does know about is a series of 1s and 0s. So every time you store a year, your computer requires, at minimum, in this encoding, this is, I'm trying to decide how specific to be. We'll just leave it at that. This would be a binary encoding of 2020. What else can we do? So this would give us binary type. These are the different approaches to binary sequence. So let's remember mathematically what's going on. Difference between binary, decimal, and hexadecimal will become important in just a moment. So I'm going to scoot my camera over. Hold on, it might be a little bit of a yucky sound, and wires need to go there. Oops, sorry, tools everywhere. So one way to think about binary is we would say each compartment is capable of having two values. So in this case, we would say binary, we can represent binary in base 2, meaning there's two possible values for every digit. Decimal is what we grew up learning, which suggests that, so we'd say that is in base 10, meaning if we have our digits of year, so then the year 2020, decimal says each bin could be any one of 10 values, 0, 1, 2, 3, through 9. So that's base 10. And so we can determine how many possible different values could be represented if we have 4 digits, each of which can hold 2 possible values. Mathematically, how many possible combinations could we have with 4 digits in binary?
$16.
Yeah, and how did you get that?
2 times 2 times 2 times 2.
Yep, or we could say 2 to the 4th. And so when, like we talked about last week, computer architectures and computer languages will define how many bits are provided for storing a piece of data of any given type. And that can vary by system. And so if you were only given a single byte of data, how many possible values can be stored in a single byte? We would calculate that with 2 to how many, so the base 2, and then how many digits do we have? We have 8 digits, and how much does that come out to? That's the magic number of?
Am I allowed to answer this one?
Nope.
64.
Nope.
No, I'm wrong.
56.
How many?
256.
256 is right. I like Wolfram Alpha a lot because it gives us a variety of outputs to tinker with. So Wolfram Alpha is a AI mathematics tool. So you can type English and it will kind of help you figure out what you meant. So we could say 2 to the 8th, and I think it'll probably figure that out. Yep, so it can process natural language. So the earliest computers stored every character on the screen using only 1 byte. So we only had a possible set of values that we could display of 256. And so early computers had to create a way of encoding human-friendly values in binary, given each character only receiving enough space for 8 bits. And so I'm going to spill it. The earliest encoding in computers, anyone know what it's called? ASCII. So ASCII stands for the American Standard Code for Information Interchange, and is known as the fundamental encoding. Technically, ASCII uses 7 of those 8 bits, and the last bit you can read the Wikipedia about how that works. But in the roughest form, here's ASCII. So encoding schemes, an encoding scheme is simply a mapping of values that are friendly to humans. In our case, we get, wait, that's not here's the official table. This is the one we want. Printable characters. Here's our binary representation using 7 of the 8 bits. And if we wanted an exclamation point, we would store off, on, off, 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 on in the computer. And so we get the simplest set of characters. We've got our uppercase, we've got lowercase, and we've got a variety of punctuation marks. So the earliest encoding was very much rooted in the Roman alphabet and languages that use that. So ASCII, we would say, is a basic encoding. This obviously presents problems when the internet went global because we ran out of encodings, or we ran out of space in the encoding table. With that, I want to try our clip for the night, which is super cool. I'm going to try a primitive way because I wasted too much time on Zoom trying to get fancy stuff to work. So I'm going to actually just play the video on a screen and point the camera at it with the sound. This is way too good. It's very rare that an ASCII table and encoding schemes are actually mentioned in a major Hollywood film. Anyone know what I'm talking about? Anyone seen it? It's nuts. When I saw it, I jumped up and down and started screaming because they actually did this on film. Matt Damon actually did it. Anyone seen it? Okay, well, this will be fun then. This will lead us into our next step.
Good Will Hunting? I don't know.
Nope, that's a good guess. That's a really good guess. So here's our encoding scheme. It'll take me a second to get this queued up. So stand by for about 30 seconds, please. And so I'm going to shut off my fan. And it's actually a really good way to learn about encoding because he's actually solving a problem using encoding. Super cool. So let's do this. And once again, as we're doing this, if something goes egregiously wrong, please chat out and I will see about problem solving. Look at that. That's easy. That's going to work. Okay. Then the video will actually be in probably roughly decent time. I need to flip the screen for a second. So setting the scene, we've got Matt Damon was on a mission to Mars, and the team was hit by a storm, and during that storm, Matt Damon got hit by an antenna, and they believed was blown off and they left him assuming he had died. Well, he hadn't died. He was left on Mars alone. And so we're going to see him try to figure out how to communicate with Earth because his antenna was destroyed. And he's going to figure out how can he communicate with NASA. Okay, so this will be a couple minutes, but I think it's worth it. So what he ends up deciding to do is dig up the Pathfinder tool. Okay, and I'll turn up the volume here in just a second.
There's nothing out there except
Okay, look what he's doing. That is encoding. Let me reframe this. Well, I mean that doesn't happen every day. ASCII tables in major Hollywood films. That made my day. Okay, so we learned a new term. We knew what an ASCII.
I think you're a lot more quiet than you were before.
Hey, your microphone is low.
I had moved my mic onto the ceiling near the speaker. Is that better? More normal me?
Not really.
Yeah, it's still pretty quiet.
Let's see if it'll auto adjust if I talk a little bit. Hold on.
Yeah.
Okay, good.
That's better. That's
Yep.
better.
Yeah, it takes a second for it to recalibrate. We learned binary is base 2, decimal is base 10, meaning 10 possible values. He used what base?
Hex, which
Hex.
is base 16.
Yes. Okay, that was your answer. Now you got to wait a half hour. So hexadecimal says we are going to store up to 16 possible values in each digit, if you will. And so for hexadecimal, the convention is 1, 2, 3, 4, 5, 6, 7, 8, 9. So there's 10, and then we need room for, we need to represent 6 more values. So we do A, B, C, D, E, and F for a total of 16 possible different values in each digit. And why is this significant? Where does 16 come from? Two to
The power of 2.
2 to the what equals 16?
It's just one more than
2 to the 4th.
Yeah, 2 to the 4th equals 16. So what that means is we can store 2 hexadecimal values in each byte. So it allows us to maximize storage at the byte level because that's how the architecture of the system works. So if we go back to the ASCII table, you'll see that we are commonly given, let me adjust this for a second. We are commonly given in ASCII both the decimal and the hex encoding of each of our values. So you can see here's binary, here's octet, so that's 8 possible values. Decimal is our human familiar, and then here's hex. So you can see the star is the first hex character is 2 and the second is A. And so that only requires 2 digits. And so we can encode more values in 2 digits with hex. And so it's also a denser way to represent binary values. So normally, if you're reading a binary file onto a screen, what you'll normally see it is in hex because you get 1 byte in 2 digits. So you'll often see this if you what are they called? Hard drive. Darn it, cluster hex. So we can probably, yeah. So if you're looking at the raw data on a hard drive, you'll see it look like this. They'll actually show you each of the clusters and then the hexadecimal values are listed. So each pair is 8 bits on the hard drive. So hexadecimal encoding is very common because it goes well with binary 2 to the 8. So why is this important in data analytics? Well, one of the most fundamental reasons is you're reading in and moving data around that could potentially be in different encodings. And so knowing what the encoding of your data is critical and can often be the source of perplexing problems until you realize that you've got an encoding issue. Now, we never figured out, ASCII isn't very kind to our friends across the Pacific that write in characters. They don't use the Roman alphabet. So we need a different encoding scheme. Anyone know what our unified encoding scheme is? Starts with the U.
Unicode.
Yeah, Unicode is the accepted standard. It's used extensively across the internet. And Unicode sets a standard for encoding, and we would say the Unicode standard is implemented, we would say, in the character encoding scheme called UTF-8. You can read a lot online describing how we would think about the differences between the idea of Unicode as an encoding scheme and UTF-8 as the actual character encoding, but that's beyond the scope of this class. So what this allows us to do is store a lot more characters. So Unicode is backwards compatible with ASCII, so it includes all of the ASCII characters, this 7 bits that ASCII used, and then it expands to include a larger width. So we can encode, this is a good example. So we can encode every known character that has been recorded in modern and ancient languages can have its own position, we would say, in the UTF-8 character encoding chart. And that's quite handy. I think it's only, it's not nearly full yet, so we can invent a lot more languages and not have any clashes with
Unicode also encodes like the entire emoji alphabet inside of it somewhere.
Yeah, absolutely. So there's plenty of room left for doing stuff like emojis that we'd expect to evolve and change with the internet for the foreseeable future. And so UTF-8 is one of the ways that most characters are encoded in modern computers. And so you'll find that in text files, you're often in a position of specifying which character encoding to use. It's often the case if you're working with legacy systems that are old, they may only have an ASCII encoding, in which case you want to make sure that you have, well, at UTF-8 would work with that, but something to keep in mind. So UTF-8 would be, so when in doubt, if you're given a drop-down box of, well, which encoding is this file in, UTF-8 would be the place to start, because it includes ASCII and then almost anything that's sent over the internet. That would be your browser standard. Questions so far in encoding? Okay, so let's try an exercise. Actually, let's not do the exercise first. So we did data encoding, so let's check off on our agenda. Let's be organized about this. So we have this idea of encoding. So we had to describe encoding. We would think about it as connecting or mapping a numeric value to a human symbol that is meaningful to humans. So it's a number symbol mapping. Now, within the data world, we're now going to move to the next level, which asks, okay, so if I wanted to write a simple character. Sorry?
Could you please enlarge the screen?
Am I still on screen share? Oh, thank you.
You're still sharing your screen to us.
Yes.
Thank you.
Oh, good. That's what I need. You got to speak up fast, just like you did. So we would say at root level, if we're using an ASCII table and I wanted to encode my, so if we encode Eric in ASCII and use uppercase, and I want to represent it in hex digits, we could look it up in the ASCII table. I could say E's hex is 4-5, capital R's hex is 5-2, and capital I is 4-9, and a C is 43. Now, it's important that I tell you that even though I'm only using decimal digits in these particular letters, the fact that it's hex is critical, because you can think about like a counter that only ticks over one more in the next column after you get to the highest level. So the decimal equivalent is not the same, even though I'm only using decimal digits in these particular letters, knowing that it's hex is critical. So if I'd go back, that the decimal equivalent of this would be, if we look it up, are different numbers because we count differently. So just, I won't go through the whole thing, but like this one is 69 in decimal and so forth. So being able to specify these will be important in our next exercise.